pause in this set of notes. So first we're going to talk a little bit about gases. Hopefully we remember that they expand to fill any container they're in, random motion of their molecules, and they're not attracted to each other. Remember, they spread out and they have the most energy of any of the states of matter. They're considered fluids, like liquids are, because there is no attraction between the molecules. Super low densities, because they don't have much of a mass. Not considered to have a volume, because they will spread out and just spread out as much as they can. And in this picture below, hopefully you remember this is solids. Strong attraction, least energy, least movement. This would be liquid. And finally gas, which are moving fastest, most energetic, and they spread out the most. Gases can be compressed, which means they can be like pushed together because there's lots of empty space between the molecules, so you can push them together. Gases undergo diffusion and effusion, which means they can move from areas of high concentration to low, and also they can go across barriers that have super small holes. In fact, if you remember back to the conservation of mass lab, a balloon doesn't appear to have spaces in between it, but it does have ridiculously small holes over time. Enough of those gas molecules can get out, and if you leave a balloon inflated over a few days, eventually it goes flat because all the gas molecules eventually can make their way through those holes. And again, their motion is not predictable, it's random. Kinetic molecular theory. Remember, kinetic means moving molecules of ideal gases. So this is like a perfect world, not what happens in real life, but in theory, particles in ideal gases have no volume. They have elastic collisions. Hopefully remember from physics, that means they bounce off each other and they exchange energy with each other, but the total amount of kinetic energy is conserved, law of conservation of momentum. All the particles in ideal gases are in constant, random, straight line motion, and they don't draw each other towards each other, attract each other, or push each other apart or repel. They have an average kinetic energy that's directly related to their temperature. As temperature goes up, so does their kinetic energy, which means they're moving faster. So higher temperatures means faster movement, which means more kinetic energy. Pause while you throw all this into your notes. Now, remember, that was about ideal gases. This is real gases in real conditions. Real gases do have their own volume. They do attract each other a little bit through intermolecular forces, the protons attracting electrons of others. Gas behavior is most ideal at low pressure. So the less pressure there is, the more they act like the slide before with ideal gases. Gases are more ideal conditions at high temperatures as well. And the reason being, at standard temperature and pressure, that's what STP means. Molecules of gases are moving fast and are really far apart, so their intermolecular forces and volumes don't even count. They exist, but they're so small we don't even count them. But at super high pressure, those gas molecules are pushed closer together, so their interactions become more significant due to that space they're taking up. And at low temperatures, they're not moving as fast, so those intermolecular forces are going to have more of an impact because the molecules are closer to each other more often. So pressure is going to be an important thing we talk about today. Pressure is force divided by area. So how much force is spread out, how much over area. It says, which of these shoes create the most pressure? Now, any girl that's worn these would definitely know, without even knowing the definition of any of this, that the high heels were. All of them would be exerting equal force because it's your weight. That would be the force that's wearing the shoes. But the area is much smaller on the high heels than it is on the shoes, and even more small than it is on the snowshoes. So that force is spread out over a smaller area. That means there's going to be more pressure. At standard atmospheric pressure, which just means when you walk outside, what's normal, the pressure of the atmosphere or the air. There's a bunch of terms, but just realize STP is standard temperature and pressure. SAP is standard atmospheric pressure. And here is some words for standard, or some figures for standard temperature and pressure. We'll talk about K here in a second, Kelvin, and here it goes. When we're talking about gases, we're always going to use the Kelvin scale, which is an absolute temperature, meaning you don't have negative numbers. The Celsius scale, related to the Kelvin. So the new scale here, Kelvin goes from 0 to 373. Those are the only temperatures that exist for us, for our purposes with gases. You can't go below 0 because at 0, it's called absolute 0 for Kelvin, things don't move. So if you would go below 0, well, at 0, they don't move, so that's the lowest temperature you can have, so you can't go below that. For Celsius, that would be considered negative 273 degrees. For temperature of freezing is 0, in Kelvin 273, and boiling point for Celsius there is 100, but 373 in Kelvin. There's a formula. We're not going to do any problems with it, but if you're given a temperature in Celsius, add 273 to it. If you're given a temperature in Kelvin, just subtract that 273, so it would be easy to work with. Lord Kelvin is a physicist who came up with this scale, and he came up with switching it to this scale because of what I said, absolute 0. It's a temperature at which particles within a gas stop moving, so the volume doesn't change. Thus, that's why they use the scale. Press pause while you put this into your notes. If you want to, Google search this and have a little song break on your own. All right, into the big picture stuff now. Gas laws. There's some different laws that relate these three variables: P for pressure, V for volume, T for temperature, and sees how they're related to it. So first law is Boyle's. This is an introduction to show you kind of understand some of this stuff. Imagine you hold the tip of a syringe on the tip of your finger so no gas can escape. If you push the plunger of this syringe, what's going to happen to the volume? What happens to the pressure? And his law says this: when you decrease the volume, you increase the collisions, thus the pressure. So look here. We can see these gas molecules are here, pretty spread out. And once we lower the volume, meaning there's less space here, now they can only fill up this much space instead of here. Well, now those same number of particles are in a smaller space, so they're going to hit each other more. And when they hit each other more, that's going to create pressure. So this sentence here is like the big thing to remember. Boyle's law says decreasing volume increases pressure. One trait goes down, one trait goes up. V goes down, P goes up. Which means they are what we call inversely proportional. As one goes up, the other goes down. This word here is important. Boyle's law is inversely proportional. Volume goes down, pressure goes up. Those are opposites, so it's inversely proportional. All right, another guy, Charles, his law says, well, before we say what it says, let's kind of see if we know that too. Imagine that you put a balloon filled with gas in liquid nitrogen. If you don't know about that, it's ridiculously cold. Like, you might have been to the science center and seen them put a tennis ball in liquid nitrogen, pull it out, and just barely touch it, and it cracks, it breaks. It's so fragile from being so cold. So if they do that, what's happening to the temperature of the gas in the balloon? Obviously, it's going way down. What happens to the volume? Well, you've probably seen it also goes way down. So here's a balloon, put it in super cold liquid nitrogen, and look how much it shrunk. The volume went down. Which means they are directly proportional, because as temperature goes down, volume goes down. The opposite is also true. As temperature goes up, volume goes up. You might notice that if you've left like a little kid's ball, or even a basketball or football or something outside on a cold night, you go pick it up in the morning, it feels a little flat. Well, that's because the temperature went down, the volume went down. If you leave it out during the daytime and it gets hot out, pick it up later, like after school, it feels like it's been pumped up again because the temperature went up, so did the volume. Direct proportional means they both do the same thing. They both go up together, or they both go down together. And here's a picture showing that. Temperature's going up. And remember, that means the molecules are going to move faster, which means they have more energy, so they spread out more, and that's why the volume also goes up. All right, Gay-Lussac's law. Third gas law we're going to talk about. Think of a balloon inside a container. So it can't get too big because it's stuck in there. So it's fully, it's blown up as much as it can be. It takes up the full amount of the container. If you heat the balloon, what's going to happen to it? Obviously, it's going to go up. What happens to the pressure of gas on the balloon? Well, we know temperature goes up, so does pressure, because the molecules move faster and push out more, spread out more. So they are directly proportional to. Temperature goes up, so does the pressure. That's Gay-Lussac's law. If you remember, we just said Charles' law also dealt with temperature. As the temperature went up, we said the volume went up. So Charles' law and Gay-Lussac's law both are directly proportional. Both deal with temperature. Gay-Lussac deals with pressure. Charles deals with volume. And here kind of summarizes them all and introduces our last law. The combined gas law combines everything we know. Talks about pressure, volume, and temperature. So just realize if you see a question that mentions all three variables, P, pressure, V, volume, and temperature, then it's got to be the combined gas law. Go ahead and put this into your notes. You won't need to use these formulas, but it might help you remember what's related. In other words, pressure and volume for Boyle, volume and temperature for Charles, pressure and temperature for Gay-Lussac, and everything for the combined law. So put this in your notes, and then you are done.